everyone! Today we're going to tackle one of the things that we love doing whenever we discuss trigonometry. We will prove trigonometric identities. This is a supplementary material to the student learning guides that you find in our KHub course Math 4 with Ma'am Sol. So what does it exactly mean when we want to prove trigonometric identities? Remember that identities are equations that are always true for any value of the variables concerned. Thus, if we are given any identity, we need to check that the expression on the left-hand side is equal to the expression on the right-hand side. If we arrive at a conclusion that they are indeed equal, then we could say that we have proven the identities. There is no only single way on how to do this, but by doing some examples in this video, I will be sharing some tips on how to make proving doable for you. Let us have our first example. Here we're going to prove that tangent theta times cosecant theta times cosine theta is equal to 1. Here we will have the first tip. Tip number 1, in proving, we should always start with a seemingly more complicated expression. In this example, we know that tangent theta times cosecant theta times cosine theta is more complicated than 1. Thus, we choose to manipulate it. But how do we do that? We now have tip number 2. We write the expression in terms of sine and cosine. We know from our ratio identities that tangent theta is equal to sine theta over cosine theta. Thus, we replace it with that. We also know from our reciprocal identities that cosecant theta is equal to 1 over sine theta. So we write it that way. Of course, we retain cosine theta. So now, by inspecting the equation, we can see that we can actually cancel out sine theta and cosine theta, and we are left with 1 in the left-hand side. This is equal to 1 on the right-hand side. Since we have concluded that both expressions are equal, we can say that we have proven the identity. The previous example was cool, right? However, not all identities come as simple as that. Some identities require a bit more of our critical thinking skills. Let's have that in our second example. Here we're going to prove that secant squared theta minus sine squared theta times secant squared theta is equal to 1. We will still apply the tips that we've learned from the previous example, and of course, add a bit more. So here, we know that the left-hand side is the more complicated expression, so that's what we manipulate. By inspection, we know that we can apply tip number 3, which is to factor some expressions. In this expression, we can actually factor out secant squared theta. Thus, we get secant squared theta times the quantity 1 minus sine squared theta is equal to 1. From our Pythagorean identities, we know that sine squared theta plus cosine squared theta is equal to 1. Thus, we know that cosine squared theta is equal to 1 minus sine squared theta. So we can replace 1 minus sine squared theta by cosine squared theta. Moreover, we learned that secant squared theta is equal to 1 over cosine squared theta. Finally, we can cancel out cosine squared theta, so we get 1 is equal to 1. And there we go, we've proven the identity. Let us try some more tips. Let's say we have this identity to prove tangent alpha minus tangent beta all over 1 plus tangent alpha times tangent beta, and we'll try to prove that it's equal to cotangent beta minus cotangent alpha all over cotangent alpha cotangent beta plus 1. You might say, easy peasy, lemon squeezy, just cross multiply. We don't do that when proving trigonometric identities. Remember that we only cross multiply when we are solving equations, which is not the case here. So what can we do? Tip number 5, we can manipulate only one side of the equation, or in some cases both sides of the equation, but separately. So how do we do that? In our equation, for easier reference, we're going to color the left-hand side red and the right-hand side green. Then we'll proceed to manipulate them individually, the left first, then the right. So let's start with the left. The expression at the left-hand side is tangent alpha minus tangent beta all over 1 plus tangent alpha times tangent beta. We will use our ratio identities to express tangent using sine and cosine. So we have for tangent alpha, sine alpha over cosine alpha, minus for tangent beta, sine beta over cosine beta, all over 1 plus tangent alpha is again sine alpha over cosine alpha, and tangent beta is again sine beta over cosine beta. Next, we will find the LCD of the fractions in both the numerator and the denominator so we can express them as a single fraction. So the LCD of the fractions in the numerator is cosine alpha times cosine beta. We will proceed using the operations like normal fractions. So you have sine alpha cosine beta minus cosine alpha sine beta. Meanwhile, in the denominator, the LCD is cosine alpha times cosine beta. And we will combine that, so we're going to have cosine alpha cosine beta plus sine alpha sine beta. From here, we can now multiply the reciprocal of the fraction in the denominator by the numerator. So you have sine alpha cosine beta minus cosine alpha sine beta all over cosine alpha cosine beta times the reciprocal, so we have cosine alpha cosine beta all over cosine alpha cosine beta plus sine alpha sine beta. So we can see that cosine alpha and cosine beta will cancel out. So we're only left with sine alpha cosine beta minus cosine alpha sine beta all over cosine alpha cosine beta plus sine alpha sine beta. This is our expression for the left-hand side. We are taking the expression in the left-hand side and we'll just put it here on the side for easier reference. Now we will manipulate the right-hand side. The expression is cotangent beta minus cotangent alpha all over cotangent alpha cotangent beta plus 1. We know from the ratio identities that cotangent is equal to cosine over sine. So we will express all cotangents as such. So we have cotangent beta is cosine beta over sine beta. Cotangent alpha will be cosine alpha over sine alpha. All over, again, cosine alpha over sine alpha times cosine beta over sine beta plus 1. Now we will take the LCD of the fractions in both the numerator and the denominator to express them as a single fraction. The LCD of the fraction in the numerator is sine alpha times sine beta. So we have sine alpha cosine beta minus cosine alpha sine beta all over sine alpha sine beta. The LCD of the fractions in the denominator is sine alpha sine beta. Therefore, we have cosine alpha cosine beta plus sine alpha sine beta all over sine alpha times sine beta. Next is we're going to multiply our numerator with the reciprocal of our denominator. So you have sine alpha cosine beta minus cosine alpha sine beta all over sine alpha sine beta times sine alpha sine beta all over cosine alpha cosine beta plus sine alpha sine beta. Now we can see that we can actually cancel out sine alpha and sine beta together. So we're left with sine alpha cosine beta minus cosine alpha sine beta all over cosine alpha cosine beta plus sine alpha sine beta, which is exactly the same as the expression in the left-hand side. Since we have proven that the left-hand side and the right-hand side expressions are equal, we can say that we have proven this identity. Let us have our last example. Let us prove that sine x all over 1 minus cosine x equals cosecant x plus cotangent x. Here we are going to manipulate the right-hand side. So we write cosecant x is 1 over sine x and cotangent x as cosine x over sine x. Then we combine the two fractions into a single one. So we have 1 plus cosine x all over sine x. We might think that we're stuck here, but what can we actually do? We have tip number 6. We can multiply by a conjugate. Why is that? Because if we do, we can apply the property of the difference of two squares. We know that if we multiply an expression a plus b with its conjugate a minus b, we will get a squared minus b squared. In this case, we will multiply 1 plus cosine x by 1 minus cosine x. So we get 1 minus cosine squared x in the numerator. Of course, we need to multiply the denominator with the same conjugate. So we have sine x times 1 minus cosine x in the denominator. And from the Pythagorean identity, we know that 1 minus cosine squared x is equal to sine squared x, so we write it that way.
Since we have sine squared x in the numerator and sine x in the denominator, then we can cancel one of them. So we have sine x in the numerator over the denominator, 1 minus cosine x. This is now equal to the expression in the left-hand side. Thus, we have proven our identity. So there we go. Those are some of the examples in proving trigonometric identities. Remember to be creative in proving. Recall any applicable formula that you might be able to think of. You can do this. See you in the next video.